We continue on with our tour of the AFNI APQC HTML. We had just gotten through the looking at the anatomical to template volume alignment here. So let's go to the next section, the vstat. So we'll look at volumetric images of the statistics data set. Up until now, everything that we've looked at would be essentially the same whether you were looking at resting state or naturalistic or task-based fMRI. This is the first part where something different happens. So we'll look later at if you're processing resting state or movie naturalistic data, something without a stimulus paradigm. In this case, when we have the vstat, what we're going to see is outputs that are related to our specific regressor stimuli of interest, and also any contrasts that we asked for. So just to mention again that we are processing task-based fMRI with an audio and a visual reliable task. Each audio and visual are actually slightly mixed in there. So there's a strong visual component along with simultaneously a weak audio one, but we just call that viz, and vice versa for the audio task. So the first thing that we'll see here when we look at this is the full fstat. So this basically tells us, highlights across the brain regions that have strong variance explained by our stimuli of interest relative to the residual, so relative to the things not explained. And we can see here that for this audio and visual task, actually this makes sense that a lot of the visual and some of the audio here in the temporal lobes, parts of the brain are associated with the task. So this is good to see. A few other things to note here just about the visualization style. It may not be immediately obvious here, but if you see there's the kind of standard coloration that we might expect. The full fstat, if you look at the color bar here, is uniformly, is positive definite, so it's 0 and just greater, so it's a kind of one-sided color bar as it were. But you can actually see there's little bits here of faded purple around, and here we actually have transparent thresholding being used. The highlight don't hide philosophy of displaying results. So when things are sub-threshold, we will still see coloration there. It just fades increasingly below the threshold. And actually in the most recent versions of the AFNI Proc quality control, the color bars that would be displayed here will actually show you where the thresholding is within the bar and how the fading looks. So here it tells us the threshold is at 25 out of this value, so it's about 1/10 of the way across here. And in this recorded video, this is a little bit older than some of this functionality, but the more modern ones will show you in the color bar explicitly. All right. There are also some regions that we see outside the brain that we shouldn't ignore. So again, this is part of the fact that even though we've estimated a mask in our processing, we're not applying the mask in our to our data. We don't want to hide away things just because they're outside the brain, because we're doing science and we want to see the evidence everywhere. So that gives us a good sense of things like signal to noise ratio, maybe motion. We might see misalignment. But there's also just the fact that magnetic effects are complicated. More than just brain active regions will show effects, sometimes due to draining veins, breathing, heart rate, all sorts of effects like that. Single subject data is noisy, so we find it useful to see what the kind of noise for a given subject looks like. So this amount of stuff outside the brain isn't particularly disturbing. Some of this may be related to draining veins, eye blinking, maybe that's related to that, and things like this. So, but within the brain, we see a lot of regions we expect, particularly in gray matter. All right, we've mentioned what the AV and the NV buttons do here. I'll just show them again quickly. This will show us our underlay and overlay in the way that we see it presented here using the same color bar. It's worth noting in the NiiVue view, the masking is actually applied, so we won't see the things outside the brain data set. And you can see the actual values, I forgot to mention this earlier, of the underlay, overlay, and threshold volumes displayed here. So the underlay value is 800. We usually don't care about that much, but if we want to know what is the full fstat here, We can see that in the overlay, the coloration. This is a special case of statistics presentation here with the full vstat, where there isn't an associated effect estimate. It's just the statistic. So we actually view the same vstat information as both the overlay and the thresholding information. We'll see below that that's not always the case. All right, and then again, if I wanted to hit C and turn on the clipping plane, I might surf through my brain. This can be useful to see things in 3D rendering. There we go. All right, and I will close that. Similarly, if I open the AV button, I'll see the expected underlay and overlay in what will be the exact same way here. And so we see the bits outside the brain and all that. And I could surf through however I wanted, investigate, see the values of the underlay, overlay, and threshold here. The usual things that we would expect in AFNI. Okay. Something that is different in this case from what we had before is we have two new buttons now. IC, and we see that this tells us this will run Instacore and GV. Let me first click GV for the graph view. What this will show in this case is that AFNI has integrated, as you're surfing with the image panels like this, you can also see the time series, the graph view of whatever you're looking at. And now I have to rearrange my panels a little bit more here. All right, so what this is showing us now is the full vstat here that we look at in this image is just a single scalar value. It's just the overlay coloration. There you go. What does it mean to be looking at a graph view associated with this data? Well, as you can hopefully read on your own computer screens if you're following along, this is showing us not the statistics volume here, but this is showing us the graph view of the residuals associated with the time series from which this vstat was calculated. So when we do our AFNI proc processing, some of the last things that we get out are the residuals from the modeling, from our regress block modeling, as well as we can have the all runs data set and the fits time series. So the fits and the ERTs. And maybe I can jump to a terminal here and very quickly show these time series here. So the all runs data set is our 3 concatenated runs, all of them together. And then this gets broken up into the fit time series, so our model fit from the regression block, and the error time series, or the residuals, which is the leftover. And here we're looking at the error time series, the residuals. So that's what ERTS stands for. The TS is time series. Okay, and coming back now to bring this back into the foreground. Here we go, our image panels and graphs again. So we're not looking at the vstat graphs here. We're looking at the EPI, the residual time series. And what we can do is we can click around and see if there's any structures that are left around in the residuals. So essentially what we hope for is this is a 5x5 montage. In this case, started in the axial, and I could turn on a graph view in any of these other slice planes if I wanted. But here I see where the 5x5 data is coming from. And these are the residuals there. Ideally, these should be unstructured and mean 0 by definition. And so as I click around, particularly in gray matter and white matter, we can see that there's a different amount of variability by this versus at the different parts of the data set. Something that might be useful, since the data has been blurred and scaled to all have mean 0, and the amount of variability is, so actually these time series now in the fit data have mean of 100, and then these, the amount of variability here is usually plus or minus a few % inside the brain. So everything looks about the same gray. What I might do is I might click the overlay and put here the ANAT final just as the overlay data set, which can help me locate where I am in the brain a little more easily, just as a visual guide. Okay, so now I can see that here, if I click in, let's go around to the visual cortex, what I might see here is indeed things are pretty flat and the amount of variability is there. Down in this corner, just around here, there's higher variability. I'm getting toward the edge of the data set and things. If I click into a ventricle, there's much higher variability compared to its kind of neighboring voxels. So some of the magnitude of variability is just explained by tissue type. What I'm happy I'm not seeing are large, very large structures and things like that. It should look kind of like a flat, fuzzy caterpillar everywhere of some kind of magnitude. The gray that you see here now appearing, if I just zoom in a little bit, zoom in and pan to where this is. So you can see that the edge of my box that I'm looking at, of the graph view selector here, includes a little bit that is, now that I have an overlay, I can see that some of this is inside where my overlay is non-zero and some of it is outside, and that's what this gray background reflects. So you can see that these 3 time series, or these 3 here, when I didn't have the overlay on, that wasn't visually apparent. Okay, but this is useful for surfing around and seeing that I don't see structures here. There's a lot of other button clicks that get mentioned here for zooming, changing the scale up and down and things like that. But essentially what we're looking for here are signs that there may be problems in the actual data, which would mean having large structures appearing here, either baseline that's not modeled well, so the mean isn't kind of zero everywhere, large changes, let's say smaller variance here, much larger variance later in time. Some of these spikes I will expect because of the motion effects. Hopefully there aren't too many, but that'll maybe appear more in other data. This data did not have a lot of motion. Okay, so that can be useful to check. Do I check that all the time? Probably not. But in particular here, since where I see strong vstat kind of makes sense visually, I will probably be happy enough, and I might not look at that always, but it's good to know it's there and its purpose. The IC button here, if I click this is also something where basically we're not processing the statistic itself here that we're looking at. We are processing, again, the residual or the ERTS data set. In this case, we're setting up Instacore within AFNI. Instacore stands for instant correlation. This is one of the most fun things you can do in data processing to visualize it. While I was talking there for a few seconds, the program, the GUI, was calculating a little bit in the background, and now it's set up and ready to go because I see some overlay here. And what is going to be displayed now is the ERTS, the residual data set, has been processed so that I'm going to look at instantly updated correlation maps of that residual data set. So now wherever I hold down, what I'm going to do is on my keyboard, hold down Shift and Control, probably with the thumb of my left hand. And now I'm going to click somewhere. And if you see, the pattern changes and updates, and there's usually a little red here and then other stuff around. What I'm seeing is a whole brain correlation to a seed at where I'm clicking in the brain. And if I remove my finger from the Shift and Control buttons and click around, I just click around. It's only when I'm holding down Control Shift together, and now I click. And this is mentioned here, how to run Instacore. There's a little tutorial here in this dialog pop-up. And you can also jump to particular locations. If you right click, you can set a seed to jump to and then set Instacore. But by and large, I invariably just like surfing around the data like this. And again, what I'm hoping for are expected patterns of correlation. So when I'm here in white matter, I really don't want to see a lot of extended correlations, just a little bit of local stuff because of blurring probably. Will there be some anti-symmetric or some symmetric things? Maybe. Actually, that is a little surprising. When I come down here to something like the visual cortex, I expect to see a lot of the visual network. Now, again, this is a little bit funny because these are the residuals of task-based data. And so in theory, there should be no structure here because it was all modeled. But in reality, the modeling is never perfect. Certainly our estimation of what a block design response is brings in assumptions, and that won't be perfect. So I would expect some structure left around from the task. Of course, when I do this in resting state data, I will be very interested in seeing the networks themselves in the similar way, even though no explicit task was given. And so there may be some of that here as well. But what I'm really looking for and hoping to avoid is some weird large artifact. And as I just click around now in some of these places where I expect activation, maybe I'm not seeing any, and that's okay. And I'm happy to see some kind of networks that I might expect. We're going to come back to this. Instacore, it's become apparent, I think, to certainly to myself and kind of most of us in the AFNI group that look at a lot of data, that this is one of the most important quality control things that you can do for your data to avoid or to know whether you have some underlying artifact in there or not. Some of the things that we look at here will hint at other possible things, but so much of what we look at are space-time patterns or spatial temporal patterns. That's kind of what regression is, seeing where we have seeing spatial locations where we have temporal responses that we expect. But there are lots of things lurking in fMRI data that can mirror that, or that can add some kind of spatial relatedness and structure. And unfortunately, some of that could even be related to a particular task design. That gets into motion-related artifacts in particular, but even some scanner ones. Particularly for event-related designs, you have to be careful about this. And by the time we look at resting state data, then it is monumentally even more important to run Instacore, because most resting state analyses are essentially looking at correlation patterns. And if you don't investigate on your own and make sure that there's nothing that looks weird in the data, you could be purely displaying results that are heavily artifactual. And we're going to see how Instacore will help, particularly with that. All right. So this IC button is really useful, even for task-based data, to have some more confidence in it. All right. Very quickly, let's look at a couple other parts of the vstat here. So this next section header, the kind of gold heading here, what are we looking at? We're looking at a presentation of the visual stimulus. So this was one of our two stimulus paradigms in this block design that was presented to the participant. And whenever we now have our regression for the main effect of the visual stimulus, we have our coefficient, our effect estimate here. So what we're looking at as the overlay coloration is the fMRI response. And because we use the scale block during AFNI proc processing, this has meaningful units of bold % signal change. And we see here in our color bar that the min and max for what we're looking at here is plus or minus 3 or 4. So, and this means that where I see red here, this is about positive 3% change, positive 3% change. Dark blue is about negative 3% or so. And so we see meaningful information by displaying with the coloration the bold % effect from this meaningful scaling to bold % signal change. The other aspect of our visualization here is the thresholding. So what we do is we highlight regions that have high statistical information, which means higher confidence in a general sense or lower uncertainty. The p-value that gets smaller and smaller as the t-stat gets larger and larger. And our thresholding here is from running a two-sided p of 0.001, the standard kind of holy value for voxel-wise thresholding. As always, we want to see more information and not be fooled by things, and also not be unstable to where the thresholding is picked. So we have this transparent thresholding of the alpha and boxed on. So everything is opaque and a little line around it, which is easier to see than up above, even though the same kind of thing was on. Where we are above threshold, and things below threshold fade away as the statistics get smaller and smaller. This is a block design. There's a large, strong response. Again, there's an audio and visual component to it in both cases for our stimulus. And we see this kind of messy stuff around the brain. That's okay. That just gives us a sense of what is the individual subject signal to noise ratio, even in kind of the air outside. And we see a little bit of noisiness inside the brain. We're maybe not used to seeing this in papers, But in papers, the thresholding is often done differently, even though we hope to change that and persuade people to do more informative results reporting. But this is also just a single subject. We know fMRI data is noisy, and this gives us a sense and a reminder of it. And we're looking really to see if there's structure out here. Otherwise, just these kind of random high and low points are fine. You can even see here that the values out here, the colors are dark red and dark blue. That just gives a sense of when you're doing a stimulus design, how much even noise can really correlate with it. It has relatively low uncertainty in things, and by the time we do group level statistics, that goes away more. So this is pretty reasonable. I could run Instacore. It's going to be the same Instacore here as it was in the previous button because it's the same ERTS or residual time series, and same with graph view. If I click the NV button or the AFNI button, I will get the same visualization as here. Again, for other technical reasons, mainly because of this volumetric view, when we look at data in NiiVue, the mask that we looked at up above that was in this section is actually applied. So just be aware of that. It's a little difference with NiiVue in particular to make this a usable image here. All right. And then as we keep going here, the second stimulus that we had in our AFNI proc command was the audio one. So now we see the response for the odd task and the same style of presentation of results, transparent thresholding, displaying the effect estimate as the overlay coloration. So this is plus 3%, let's say, and this thresholding based on the statistic with two-sided testing, because that's what we pretty much always have as our hypotheses of interest, is something different than zero. That's a two-sided hypothesis. We also, in our AFNI proc command that we looked at just briefly in the beginning of this, there is a contrast that we modeled, that we specified in AFNI proc itself. So we asked for the difference between the vis and odd. So where is v minus a, vis minus odd, far away from zero? And that's what we're looking at here. Again, this is a t-test type question, so we look at the coefficient. So we have the coloration interpretation that this is where the difference is positive and about here when we see the color bar range, let's say 2.5. So here, this means that the visual response, beta weight, is about 2 or 2.5 or so, excuse me, bold percent units larger than the audio response. Here, when it's blue, dark blue, then this means that it is also a difference of about 2 or 2.5, but it's negative. That means the audio is bigger. So where things are hot colored, visual is greater than audio because it's positive. For this kind of contrast setup, V minus A is positive. That means V is bigger than A. And where we see blue, A is bigger than V, so it's negative. And then you can see the size scale there. And then finally, we had also included just the mean audio-visual response. Again, everything that we've built up to here holds. Transparent thresholding, you can see the scale of this. This is still units of bold percent signal change for an average response. Not even average magnitude, but just the average of the beta weights for mean and odd. I don't know that we particularly use this, but it was just another example of a contrast, a general linear test that we could set up. Okay, and that's the end of the vstat section here, so I'll pause and we'll continue on in another video.